The universe had a clear story, 13.8 billion years old, slow, orderly, and predictable. But we were wrong, utterly and completely. Because, when the James Webb Telescope ripped through the curtain of time, it found things that shouldn't be there. It discovered massive galaxies just 300 million years after the Big Bang, a mere 2% of the universe's entire history. These galaxies held billions of stars. But this was impossible, because, according to our current physics, they needed at least 2 billion years to form. This is why all our models became meaningless in an instant. But that wasn't the most disturbing part. These impossible galaxies were surprisingly common. This raises the question, what if everything began wrong? If you too are wondering what the true beginning of the universe might be, then like this video and subscribe. Because the history of cosmology as you know it is being rewritten right now. Here we go. We thought the universe had a clear story, a 13.8 billion year old story, slow and orderly. It had a predictable beginning. The foundations of the cosmos were solid. But we were wrong, terribly wrong, because when James Webb ripped through the veil of time, it found galaxies there, just 300 million years after the Big Bang, that should not have existed. These structures had billions of stars. But this was impossible. Physics dictated that they needed at least 2 billion years to form. The very foundations of the universe trembled that day. But the real shock was just how common these impossible galaxies were. And this gave birth to the question that changes everything. What if it all started wrong? This is why Webb is so much more than a telescope. It is a time machine. And this is not a metaphor. It is the literal truth. Because light, despite all its speed, is not instantaneous. Even at its staggering speed of 300,000 kilometers per second, its journey through space takes time. This delay transforms the entire universe into a kind of history museum. Every object we see is frozen as it was when its light began its journey towards us. The closest example is the moon. The reflected sunlight leaves its surface and reaches us just over 1 second later. So when you look at the moon, you see it as it was 1 second ago. The sun is farther away. Every time we look at it, it is already about 8 minutes in the past. The nearest star, Proxima Centauri, is more than 4 light years away. This means that when its light began its journey, you could have been in a completely different phase of your life. Yet, these scales are nothing compared to the distances Webb deals with. The Andromeda galaxy is visible to the naked eye, but the faint light that enters your eye left that galaxy 2.5 million years ago. The image you see is older than the entire history of human civilization. It is this layered structure of time that makes astronomy so extraordinary. Because you can never see the universe as it is now. You can only see it as it was in the past. But to look deep, it's not enough to just look far. You also need to see the invisible. The reason for this is cosmic expansion. Since the Big Bang, space itself has been expanding, and the light that has travelled through it for billions of years stretches along with it. Its wavelength gets longer. What started out as ultraviolet or visible light from the first galaxies is pulled and shifted towards the red end of the spectrum over its billions of years of travel. By the time it reaches us, it is no longer visible light. It has become infrared light. To capture this light, you need an eye tuned to these long wavelengths. Hubble could peek into this region a little, but not far enough. But Webb was designed entirely with this idea in mind. Its massive 6.5-meter golden mirror, made of 18 hexagonal segments, collects far more light than Hubble's 2.4-meter mirror. A bigger mirror means more light. More light means you can detect fainter and more distant objects. This isn't just about seeing better. This is about seeing what was once completely invisible. That is why James Webb is not just a more advanced version of Hubble. It is a complete revolution in the way we see the universe. So what did this revolutionary eye expect to see when it looked into the darkest period of history? For the answer, we must go to the most mysterious and empty period of the universe, the cosmic dark ages. This name may sound poetic, but it's actually a very technical description. About 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms, it became transparent for the first time. The light released at that moment is what we see today as the cosmic microwave background radiation. But what happened after that moment? The universe was plunged into a pitch-black darkness, filled entirely with neutral hydrogen and helium gas. There were no stars, no galaxies, just silence and darkness. This period lasted for about 400 million years. That's more than twice as long as the dinosaurs ruled the Earth. During this time, gravity worked silently, slowly pulling gas clouds into denser regions. But this process was expected to be very slow. The end of these dark ages could only come with the ignition of the first stars. This process of illumination is called the epoch of reionization. When the first stars and galaxies formed, their intense ultraviolet light began to reionize the neutral hydrogen gas around them, stripping the electrons from the atoms once again. The universe began to light up in small bubbles. Over time, these bubbles grew, merged, and eventually covered the entire universe, bringing it to its current ionized, transparent state. This entire theoretical framework has been the foundation of cosmology for decades. Each piece followed the other in a logical sequence. Everything was supposed to proceed slowly and predictably. First, a calm beginning defined by the cosmic microwave background radiation. Then, hundreds of millions of years of deep silence and darkness, the cosmic dark ages. And finally, a cosmic dawn that tore through this darkness with the violent light of the first stars, the epoch of reionization. But now that we have completed this conceptual preparation, we can get to the real question. The reason we sent a multi-billion-dollar telescope into that void. When James Webb looked at that boundary where theories end and observation begins, at those first galaxies, those early formed stars, those seemingly impossible black holes, what did it truly find? Because what Webb found were not just photos that didn't fit our slow growth story. What Webb found, from the very beginning of the universe, was an unexpected maturity, an inexplicable size, and an unimaginable complexity. That is why what Webb showed us is that the universe, from its very beginning, was far busier, far faster, and perhaps far more creative than we ever thought. And all of this is wrapped in a delicate paradox. Because, no matter how unsettling these discoveries are, they also remind us of just how much more we have to learn. If Webb has taught us anything already, it's that the cosmos is far more dynamic than our textbooks, and perhaps even more surprising than our imagination. It is not just filling in the gaps, it is questioning the foundations. But at the center of this questioning lies a single key, that magical mechanism that emerges when Webb's infrared eye combines with its ability to travel through time: cosmic redshift. This is the process that unlocks the deepest secrets of the universe, that shapes everything Webb sees, and that pushes it to rewrite our history of the universe. Because Webb isn't just looking back billions of years, it's looking at light that has been stretched, made unrecognizable by the expansion of the universe. Without this stretching, there would be nothing to see. That's why, to understand the shocking things Webb found, we must first understand this incredible journey of light, a journey that begins as a bright blue star and ends billions of years later as a faint invisible infrared photon on Webb's golden mirror. And the story these photons tell changes everything we thought we knew. Because those redshifted photons are not just an image, they are proof of the universe's expansion history, of the most fundamental laws of physics, and of the very fabric of time. That is why every galaxy Webb observes is not just a bright smudge, it is also a cosmic clock. And the time these clocks are showing does not match our own. But to understand the origin of this discrepancy, we must return to the starting point of everything, to that initial moment that this entire story references. Without that reference, we cannot correctly place either the dark ages or reionization. This reference point is the cosmic microwave background radiation, or CMB for short. It is the baby picture of the universe. It is the fossilized light released just 380,000 years after the Big Bang, when the universe ceased to be a ball of plasma and became transparent. This light, which has been traveling through space for 13.8 billion years, has stretched so much with the expansion of the universe that it no longer reaches us as a warm glow, but as a freezing -270 degrees Celsius microwave signal. This CMB map is one of the most precise things we know about the universe, and it shows that the universe is almost perfectly homogeneous, but with tiny temperature fluctuations of 1 part in 100,000. These tiny fluctuations are the seeds of everything. They are the initial density differences where gravity would later gather matter to create galaxies, stars, and us. Our standard cosmological model, the Lambda-CDM model, is built upon this CMB data. The model predicts with incredible success how these tiny fluctuations grew to form the universe we see today. But there's a problem. This model says that growth should be slow and hierarchical. Small structures form first, then they merge to form larger ones. The model starts from that calm and orderly beginning presented to us by the CMB. But the galaxies Webb found are not calm and orderly. They form too early, too large, and too actively for this calm beginning. This is where the greatest tension arises. We have the most reliable baby picture of the universe, but the early adolescent pictures Webb is showing us don't explain how that baby could have grown up so fast. This situation has pushed some to a radical idea, the thought of reconsidering the age of the universe. This is not a mainstream view, but Webb's data is so jarring that some scientists are not shying away from asking the most audacious question. What if the universe is older than 13.8 billion years? For example, Rajendra Gupta from the University of Ottawa has developed a model suggesting the universe could be 26.7 billion years old. How could this be possible? This model proposes a universe where fundamental physical constants, like the gravitational constant, change over time. If these constants were different in the past, then our way of interpreting redshift also changes. This would mean that distant galaxies could be older than we thought. This model could easily explain why the first galaxies look so mature, because it gives them billions of more years to develop. But this idea faces a huge problem: the cosmic microwave background radiation. The CMB data is in incredible agreement with an age of 13.8 billion years. Therefore, doubling the age of the universe risks breaking this perfect harmony with the CMB. This is one of the greatest dilemmas of modern cosmology. On one hand, Webb's impossible galaxies, and on the other, the Planck satellite's flawless CMB map. Both are real, but it seems they cannot both be true at the same time. It is this tension that now takes us beyond theories and models into the shocking world of concrete discoveries. Because what we are about to tell you are no longer simulations or predictions. They are the oldest secrets of the universe, carried by the photons that fell on Webb's golden mirror. And when Webb looked at that moment where theories, simulations, and decades of patient waiting ended, when the telescope turned its eyes to the dawn of the universe, what it found was not just an anomaly, but a revolution. Because now comes the real shock. Get ready. We are no longer talking about concepts, but facts. Here is what Webb found. The first shock was the galaxies that shouldn't exist. At least, not like that. They were massive cities of stars shining when the universe was only 300 to 400 million years old. This was a blink of an eye on the cosmic timeline. Just 2% of the universe's 13.8 billion year history. But the problem wasn't their age, it was the galaxies themselves, their brightness, their size. When astronomers looked at this initial data, their reaction was complete shock, because this had to be a mistake. Perhaps the telescope was confusing closer, dusty objects with very distant galaxies. But Webb's precise spectroscopy came into play. The redshift values were measured, and the numbers did not lie. Some galaxies had a redshift above Z equals 13. This meant their light had travelled for more than 13.4 billion years to reach us, and they were truly gigantic. This is why the standard cosmological model, the Lambda-CDM model, took its first major blow here, because this model says that structures form from the bottom up, slowly. First small star clusters, then dwarf galaxies, and then, after billions of years of mergers, large galaxies. But Webb had found a metropolis full of skyscrapers in an age when only the foundations should have been laid. The laws of physics should not have allowed so much matter to accumulate so quickly in that young age of the universe. This wasn't just filling a gap, it was like tearing out the first page of the book, but the real impossibility was hidden inside these galaxies. Webb didn't just look at the galaxies, it also looked at the stars within them, and what it found was even more mind-boggling. Inside these earliest galaxies, there were chemically mature stars. What does this mean? When the universe formed, there was only hydrogen, helium, and a tiny amount of lithium. The first stars, the theoretical population 3 stars, should have been formed only from these pure materials. Heavier elements like carbon, oxygen, and iron, everything astronomers call metals, had to be forged in the cores of these first stars and then dispersed into the universe when they died as supernovae. Only the second generation of stars could contain these metals. This process was supposed to take hundreds of millions of years. Webb found traces of metals in galaxies shining when the universe was only 300 to 400 million years old. This implies a time compression that defies reason. Because this means not only had the first stars formed, but they had also lived for millions of years, completed their life cycles, exploded, and their debris had recondensed to form new stars. And all of this had happened hundreds of millions of years before theory allowed. Scientists were stunned. It was like a newborn baby reciting its grandfather's memories. There was a life that needed to be lived in between, a generation that had to pass. But that generation was missing from the timeline. It was as if the universe had skipped a few steps in its evolution and gone straight to the conclusion. This discovery screamed that our models of star formation were either completely wrong or catastrophically incomplete. And just when things couldn't get any stranger, black holes entered the scene. But these were not the normal black holes formed from the death of stars. They were monsters, supermassive black holes with millions or even billions of solar masses. And they appeared at the dawn of the universe, billions of years before they were supposed to. According to our current understanding, a black hole starts with a stellar mass and grows slowly by swallowing surrounding gas or merging with other black holes. Sagittarius A star, at the center of the Milky Way, took more than 13 billion years to reach its 4 million solar masses. But Webb found black holes that had reached 10 million, 50 million, or even billions of solar masses when the universe was not even a billion years old, only 700 to 800 million years old. This seemed physically impossible. Because there is a limit to how fast a black hole can grow. It's called the Eddington limit. If it tries to feed too quickly, the radiation pressure from the infalling matter pushes away more matter from falling in. It's a self-regulating process. But these monsters Webb found seemed to completely ignore this limit. It was as if they were born as full-grown adults. This situation brought exotic theories like direct collapse back to the forefront. Perhaps these black holes didn't form from stars. Perhaps giant gas clouds collapsed directly onto themselves, creating seed black holes of tens of thousands of solar masses. But even this is not enough to explain the observed massive sizes in such a short time. This discovery questions not only galaxy formation, but everything we thought we knew about the most fundamental workings of gravity. Therefore, when these discoveries are put together, the picture that emerges is this. Giant galaxies that theoretically shouldn't exist. They host stars that are impossible to be in them, and at their centers, they are ruled by monster black holes that defy the laws of physics. These are not 3 independent anomalies. They are 3 pieces of an interconnected puzzle, all pointing to the same startling truth. Our story about the beginning of the universe is collapsing from its foundations. This is not a problem that can be solved by fixing 1 or 2 theories. This is a crisis that requires us to rethink the entire structure. Because these discoveries leave not only the when and how much questions unanswered, but also the most fundamental question, how? And the answer to this how question may take us to much stranger places than we expected. Because the structures Webb found are not only large and early, but also strangely orderly and unexpectedly mature. And this maturity suggests that the problem is not just one of timing, but perhaps that there is a hidden ingredient in the initial recipe of the universe that we never knew about. Because if this was the recipe, the resulting product should have been completely different. But there they are, right before Webb's eyes, challenging all our theories. Perhaps there is a common mechanism underlying all these anomalies. Because the real problem is not that these pieces exist individually. The real problem is that they all appear at the same time, in the same place, like a cosmic conspiracy. And this conspiracy pushes us to question one of our most fundamental units of measurement, the timeline of the universe itself. Because these massive structures found by Webb are not just early, they are also creating a cosmic crowd. The early periods of the universe seem much denser and much more crowded than models predicted. It's as if 1,000 people showed up to a party where only 100 were invited. This situation leads us to another shocking discovery, an order that overturns theories. It's not just the large galaxies, their structures also challenge the theories, especially the existence of disk galaxies. Disk galaxies like the Milky Way are thin, orderly, rotating disks of stars. The formation of these structures requires an extremely delicate and slow process. It requires gas to slowly settle into a plane over billions of years, conserving its angular momentum and avoiding violent mergers. That's why astronomers did not expect to find disk galaxies in the early universe. The early universe was supposed to be a chaotic and violent place, with constant mergers and collisions. In this environment, galaxies were expected to have irregular, lumpy shapes. But Webb found surprisingly well-formed disk galaxies when the universe was only 600 million years old, right in the middle of the epoch of reionization. One of these is a galaxy with the reference Cheers 13.316. This galaxy is estimated to have a mass of about 30% of the Milky Way's disk, and this is at least 1 billion years earlier than theoretical models allow. It was like finding a perfectly built glass palace in the middle of a sandstorm. The environment should not have allowed such a delicate structure to form. This discovery shows that our galaxy formation simulations may be fundamentally wrong. Perhaps gas is collapsing in a much colder and more orderly way than we thought. Or perhaps there is a feature in the structure of dark matter halos that supports the disk-like collapse of gas. In any case, these impossible disks are one of the most striking proofs of how quickly the universe can extract order from chaos. And this order appears not only on a galactic scale, but on even larger scales. Because perhaps the most surprising of these discoveries are not the individual objects, but the way they come together. Webb is finding the first seeds of massive cosmic structures, namely galaxy clusters and protoclusters. In the first few 100 million years of the universe's history, it is even observing the first nodes of that giant filamentary structure that envelops the universe and is known as the cosmic web. For example, Webb discovered a protocluster called J1000+0234, a structure with 10 confirmed galaxies and hundreds of candidates just 830 million years after the Big Bang. This structure has the potential to reach a total mass about 10 times that of a modern galaxy cluster, like the Coma cluster. But for so many galaxies to be gravitationally bound to each other in such a short time, again contradicts the predictions of the standard model. According to the Lambda-CDM model, the formation of such large-scale structures requires much more time, because gravity acts slowly over these vast distances. The existence of these early proto-clusters suggests that the initial density fluctuations, those tiny seeds we see in the CMB, were perhaps larger than we thought, or that dark matter, the invisible scaffolding that holds these structures together, worked faster and more efficiently than expected. This is like seeing not just a single building, but an entire city built centuries ahead of schedule. And this even questions one of the most fundamental principles of cosmology, the assumption that the universe is homogeneous and isotropic on large scales. In conclusion, the picture Webb presents to us is clear. Massive galaxies that theoretically shouldn't exist. They host chemically enriched stars that are impossible to be in them, supermassive black holes that defy the laws of physics, and all of this appearing in a surprising order and structure in an era that should have been chaotic. These discoveries are not disconnected puzzle pieces. They are like different instruments in the same orchestra, all playing the same startling melody. Our story about the early universe is wrong, and this error is not in a minor detail, but in the fundamental structure of the story. But how can this telescope see such distant, such faint objects so clearly? What is the secret behind that incredible technology? Those golden mirrors, those freezing cold sensors? What enables it to make these impossible measurements? Because, to understand these discoveries, we must first understand the engineering marvel that made them possible, James Webb itself. We need to know how it works, how it captures light, and how it transforms those photons into numbers, into meaning for us. Because the magic is not just in what it found, but also in how it found it. And this technology, in itself, is like the pieces of a puzzle. But how does all this magic work? How can we see such distant, such faint, such impossible objects so clearly? Because the James Webb Space Telescope is not just a bigger telescope, it is the culmination of decades of engineering and physics genius. Now let's slow down the tempo a bit. Let's move away from the headlines of those shocking discoveries and look under the hood of the incredible technology that made them possible. Because, without understanding how this engineering marvel works, we cannot fully grasp how revolutionary its discoveries truly are. It all starts with Webb's eye, its giant primary mirror. This is not just a large piece of glass, it is a foldable origami work of art made of 18 separate hexagonal segments. It had to be folded to fit into the launch rocket, and after reaching space, it had to open flawlessly to form a single, giant mirror with a total diameter of 6.5 meters. This mirror has about 6.25 times more light-collecting area than Hubble's 2.4-meter mirror. It's like collecting rainwater with a bucket. The wider the bucket, the more water you collect in the same amount of time. Webb's bucket is so huge for exactly this reason. Because the photons, the particles of light, coming from a galaxy 13 billion light-years away, are incredibly rare. In 1 second, only a few photons from these galaxies hit Webb's mirror. That's why it's vital to capture as many photons as possible. But the real genius of this mirror lies in its material. The segments are made of beryllium because beryllium is both extremely light and an incredibly stable metal that can maintain its shape in the freezing cold of space. Each segment was polished with atomic-level precision and then coated with a very thin layer of gold. So why gold? Because gold is extraordinarily efficient at reflecting not visible light but infrared light, Webb's main prey. The gold coating reflects more than 99% of the incoming infrared photons, directing them to the secondary mirror, and from there to the scientific instruments. Hubble's mirror was coated with silver and was less efficient in the infrared spectrum. That's why Webb's mirror is so effective, not just because it's bigger, but because it was specifically designed for infrared light. It is a giant ear that can hear even the faintest whispers of the universe. But this giant ear can be disturbed by even the slightest noise around it. And the biggest noise in infrared astronomy is heat. Heat is infrared radiation. The telescope itself, if not cold enough, would emit so much infrared light that it would drown out the faint cosmic signals it is trying to capture. It's like trying to hear a whisper in a stormy sea. To hear the whisper, the sea needs to calm down. For Webb, this calmness is provided by its giant sunshield. This is perhaps the most ingenious and riskiest component of the telescope. It is a 5-layered membrane the size of a tennis court, incredibly thin. Each layer is made of a special polymer called kapton and is thinner than a human hair. These layers are designed to block the heat and light from the sun, the Earth, and the Moon. The sun-facing side of the sunshield heats up to about 85 degrees Celsius, while the other side in the shadow, where the telescope's mirrors and instruments are, drops to a freezing temperature of -233 degrees Celsius. This is a temperature difference of almost 320 degrees, and what creates this difference is the vacuum between the layers. Heat dissipates in these gaps as it passes from one layer to the next, weakening at each layer. By the end of the fifth layer, the thermal energy reaching the telescope is reduced to 1/millionth. Without this incredible insulation, Webb's sensitive detectors would be blinded by their own heat. Hubble didn't need such a shield because it was in low Earth orbit and worked mainly in visible light. Webb is positioned at the L2.1.5 million kilometers away from us. This point ensures that the Sun, Earth and Moon always stay in the same direction. Thus, Webb can keep its shield constantly facing these heat sources and protect its mirrors by keeping them forever turned towards the cold, dark space. This shield is the indispensable darkroom that allows Webb to see. Another reason Webb is so sensitive is that it not only collects light, but also analyzes it. And this task is performed by the four main scientific instruments located behind the telescope. They are the telescope's brain. One of the most important instruments is NIRSpec, the near-infrared spectrograph. A spectrograph separates light into its component colors, a spectrum, just like a prism creates a rainbow. But these cosmic rainbows tell us not only how bright a galaxy is, but also what it's made of, how fast it's moving, and how far away it is. NIRSpec's revolutionary feature is its use of a technology called a micro-shutter array. This is a postage stamp-sized grid of about 250,000 tiny windows. Each window can be opened and closed individually. Thanks to this technology, astronomers can take the spectra of more than 100 different celestial objects at the same time. With Hubble, it would have taken years to get the spectra of the hundreds of galaxies in a single deep-field image, because Hubble could only focus on one object at a time. But NIRSpec incredibly speeds up this process by opening the microshutters over the interesting galaxies in its field of view and closing the rest to block unwanted light. It's like turning up the volume of only the people you want to listen to in a crowd and muting everyone else. This multi-object spectroscopy capability has enabled Webb to analyze the chemical composition and distance of so many early galaxies in such a short time. That's why the evidence for those impossible metals and record-breaking redshifts was obtained thanks to this revolutionary capability of NIRSpec. But Webb's vision is not limited to the near-infrared. It needs to extend to even longer wavelengths, the mid-infrared range, where the dustiest and coldest objects of the universe are hidden. This task falls to MIRI, the mid-infrared instrument. MIRI is the coldest part of Webb. While the other instruments passively cool down to -233 degrees Celsius, MIRI needs to be even colder. Because longer infrared wavelengths mean lower energy photons, and to detect these photons, the thermal noise of the detectors must be at an absolute minimum. That's why MIRI is actively cooled down to -266 degrees Celsius, just 7 degrees Celsius above absolute zero, using a special cryo-cooler system. This is one of the coldest known places in the universe. Thanks to this extreme cold, MIRI can see things that no other telescope can. For example, it can penetrate into the dense dust clouds where stars and planets are forming. These dust clouds are completely opaque in visible light, and even in the near-infrared, meaning they don't show what's inside. But MIRI's mid-infrared vision allows it to see behind this dust, just like an X-ray machine sees inside our body. This way, MIRI can study the structure of protoplanetary disks, the traces of molecules like water vapor or methane in the atmospheres of exoplanets, and the hidden cores of the oldest, dustiest galaxies. Hubble had almost no vision in this range. There was the Spitzer Space Telescope, but it was much smaller and less sensitive than Webb. MIRI increased Spitzer's resolution by about 10 times, and its sensitivity by more than 100 times. That's why the window to the universe's most secret birthplaces and dustiest secrets is MIRI's freezing eyes. But when all these mechanisms come together, James Webb emerges. It's when all these parts, the massive golden mirror, the ultra-cold sunshield, the multi-object spectroscopy, and the cryo-cooled mid-infrared vision combine that they form Webb. These are just the main parts. There are also the fine guidance sensors that lock the telescope onto its target. the communication systems that send data to Earth, and the software that manages this whole complex operation. Because the real power of the telescope is not in a single part, but in the symphony created by these parts. So how do the magnificent images created by this symphony emerge? How do that raw data, those numbers, transform into the breathtaking colours we see? Because those colours are not just an aesthetic choice, they are science itself. The vibrant reds, blues, and greens in the images captured by Webb are not an arbitrary colouring by the telescope. They are a way of translating the infrared world, which the human eye cannot see, into a language we can understand. This process, known as colour assignment, is one of the fundamental steps in interpreting Webb's data, because Webb basically takes black and white photos in different infrared colours, that is, at different wavelengths. For example, when photographing a galaxy with NIRCam, the near-infrared camera, it does so using different filters. Each filter allows only a specific range of infrared wavelengths to pass. For example, one filter captures light around 0.9 microns, another at 2 microns, and another at 4.4 microns. This means having several grayscale images of the same object taken in different colours. Image processing specialists then take these grayscale images and assign a colour from the visible spectrum to each one. Usually, blue is assigned to the shortest infrared wavelength, green to the middle, and red to the longest. When these three colour images are combined, those breathtaking, colourful cosmic landscapes emerge. This is not just an aesthetic choice, it is a scientific tool. And because different chemical elements, gases at different temperatures, and stars of different ages appear brighter at different infrared wavelengths. For example, active star-forming regions often glow in the mid-infrared seen by MIRI, and are represented as red. Older star populations are more prominent in the near-infrared seen by NIRCam, and usually appear blue or white. Therefore, by looking at the colour distribution in a Webb image, we can instantly understand which regions of a galaxy are younger, which are dustier, or which have shockwaves. Hubble also used colour assignment, but it usually combined visible light filters. Webb's colour palette, however, represents a completely different world, the invisible infrared universe. That's why Webb's colours are so effective, not just because they are beautiful, but because they visualise physical processes we cannot see. But Webb has another superpower, the ability to track not just stationary objects, but also moving and changing objects with incredible precision. This task is undertaken by FGS/NIRS, the Fine Guidance Sensor / Near-Infrared Imager and Slitless Spectrograph. The main job of FGS is to keep the telescope locked on its target with millimeter precision, just like a car's lane-keeping assist. It locks onto a guide star and corrects even the slightest deviation of the telescope with a precision of a millionth of a second. This is vital, especially for long exposures, because even the slightest vibration would blur the image. But its partner NIRS does much more. NIRS is specifically designed to study exoplanets, planets orbiting other stars. It does this with a technique called transit spectroscopy. As an exoplanet passes in front of its star, it blocks some of the starlight, causing a tiny dip in brightness. From the size of this dip, we can understand the size of the planet. But NIRS does much more by separating this light into a spectrum. Because some of the starlight filters through the planet's atmosphere to reach us. Any molecules in the planet's atmosphere will absorb specific wavelengths of the starlight, creating dark lines, absorption lines, in the spectrum. NIRS can detect these tiny absorption lines. It's like understanding what the air in a room is made of by looking at the changes in the colours of the light seeping through its window, without seeing inside the room. Thanks to this technique, Webb has already detected molecules like water vapour, carbon dioxide, methane, and even sulfur dioxide in the atmospheres of planets tens, hundreds of light years away from us. Hubble could also use this technique, but Webb's much larger mirror and infrared sensitivity have made these measurements 10 times more precise. Webb can detect a molecule in an exoplanet's atmosphere, even if it's present in a ratio of 1 part per million. That's why, in a journey to search for chemical signs of life on other worlds, this incredible sensitivity of NIRS is our most powerful tool right now. But behind all these incredible instruments and mechanisms lies what is perhaps one of Webb's least celebrated but most important achievements: the launch and deployment process. Because Webb was so large and complex that it couldn't fit fully deployed into any rocket's cargo bay, so it was launched folded up like a beehive and had to unfold itself flawlessly in the vacuum of space, 1.5 million kilometers from Earth. This was one of the most complex robotic operations in history. There were over 300 single points of failure during this process. This meant that if just one of these 344 steps went wrong, the $10 billion telescope would become space junk, with no astronaut who could go to fix it. Everything had to work perfectly. And it did. First, the sunshield slowly unfolded, layer by layer, and was tensioned. This operation alone took a week and required 107 separate mechanisms to work flawlessly. Then the secondary mirror settled on a tripod, and finally, the two side wings of the primary mirror locked into place. The entire process took about a month. It was a month of held breaths, where the decade-long work of tens of thousands of engineers and scientists depended on a single mistake. The success of this deployment is not just an engineering triumph, it is also a testament to human ability in planning, simulation, and rigorous testing. When Hubble was launched, a flaw was discovered in its mirror, and it had to be repaired by astronauts. That incident was a big lesson for NASA. That's why every single part of Webb was tested countless times on Earth, in giant vacuum chambers and on vibration platforms that simulate space conditions. This meticulousness was the greatest assurance behind the perfect Christmas Day launch of Webb and the flawless deployment process that followed. That's why when we look at each of Webb's images, we see a reflection not only of the universe, but also of human ingenuity and perseverance. But the most exciting thing is that this machine not only answers the questions we expected, but also raises new questions we didn't expect, questions we didn't even think to ask. And now that we understand how this incredible machine works, we can return to the heart of those shocking discoveries, to the depths of those impossible galaxies and monster black holes. And because this technical foundation now prepares us for a much greater climax, for the most intense moment of that great war between theories and observations. And now, the real miracle comes now. Everything we've told you so far was just a preparation, a warm-up lap. Because now we come to those moments where theories and models completely collapse, where the limits of the human mind are pushed to the climax, to the most incredible, most shocking, most epic discoveries of the James Webb Space Telescope that have forever changed not just the books of cosmology, but also our relationship with the universe. Now hold your breath, because we are taking the tempo to its peak. No more slow explanations, just pure, raw, shocking facts. This is the front line of science, and here anything is possible. The first bombshell, its name, JADES-GS-Z-13-0. This isn't just a galaxy, it's a ghost, an entity that should not exist. Webb saw it, and the scientific world froze. Because the light from this galaxy reached us from a distance of 13.4 billion years. This means it was shining when the universe was only 325 million years old. 325 million years, just 2.3% of cosmic history. But that wasn't the problem. The problem was the galaxy itself, its brightness, its size. When astronomers first received the data, they thought it was a mistake. Maybe a closer star, a foreground object, was contaminating the image. But the spectroscopy results came in. The redshift was certain. Z equals 13.2. This was the highest confirmed redshift in history. It was officially the most distant and oldest galaxy humanity had ever seen. So how could it be so bright? This galaxy appeared to have formed hundreds of millions of solar masses of stars in just 325 million years. This meant a star formation rate at least 10 times faster than theories allowed. The standard Lambda-CDM model said that such an efficient star factory could not exist in that era. It was like building a skyscraper in a day. No material, no time. It was physically impossible. But there it was. When this discovery was published in the most prestigious journals like Nature Astronomy, it caused an earthquake in the scientific world. The articles asked, how can we reconcile this galaxy with our models? The answer was simple. You can't. JADES-GS-Z-13-0 single-handedly shattered all our comfortable assumptions about the early universe. It was not an anomaly, it was the first herald of a new rule. But Webb didn't stop. It looked deeper, and it found something even more incredible: Schrödinger's galaxies. This isn't an official name, it's a nickname given to them by scientists in shock. Because these objects seem to both exist and not exist at the same time. When Webb looked into the first 500 to 700 million years of the universe, it discovered 6 giant galaxy candidates. They were so large that if their redshifts were confirmed, they alone would account for the entire mass assumed to exist in the universe at that age. This was impossible. It was like all the air in a room gathering in one corner. The statistical probability was 0. One of these galaxies, JADES-GS-Z-11-0, already appeared to have hundreds of billions of solar masses. That is, the same mass as today's Milky Way. But when the universe was only 450 million years old, how could this be possible? The leader of the team that made this discovery, Joel Leisure, said he felt sick to his stomach when he first saw the data, because it seemed like a violation of the laws of physics. The stellar mass found in these galaxies exceeded the total amount of baryonic matter that was thought to exist in the universe by that time. That's why they were called Schrödinger's galaxies. Because, on one hand, the data was there, and on the other, their existence was impossible. There were 2 possibilities. Either these objects were not galaxies, but quasars, gas clouds around supermassive black holes that were unbelievably more massive than anything we had ever seen. Or the standard cosmological model, Lambda-CDM, was fundamentally, catastrophically wrong. This discovery split the scientific world in 2. On one side were those who hoped the data was some kind of error, and on the other were those who declared that a new revolution in cosmology had begun. These 6 galaxies were 6 time bombs placed at the heart of cosmology, and time was ticking. And just as the shock of these bombs had not yet subsided, Webb revealed the darkest secret: a black hole. But not an ordinary black hole, the oldest, most distant supermassive black hole in history. At the center of a galaxy called CEERS 1019, this galaxy was shining just 570 million years after the Big Bang, and the black hole at its center was a full 9 million solar masses. 9 million. Think about that number for a moment. The black hole at the center of the Milky Way took 13 billion years to reach its current 4 million solar masses. But this black hole had reached more than twice that mass in just 4% of the universe's age. This meant completely shattering the theoretical limit of a black hole's growth rate, the Eddington limit. This black hole was swallowing an incredible amount of gas every second. But how did it manage to grow so big so early? Standard stellar seed models couldn't explain it. Because, for a seed of 30 to 100 solar masses formed from the death of a star to reach 9 million solar masses in such a short time, it would have to feed at a rate thousands of times higher than the Eddington limit, a physically impossible rate. That's why this discovery provided the strongest evidence for the direct collapse theory. Perhaps this black hole was born as a heavy seed of tens of thousands of solar masses from the direct collapse of a giant gas cloud. But even this is not enough to fully explain this extraordinary growth. The black hole of CEERS 1019 is not just a record, it is evidence that shakes our fundamental understanding of how monsters are born at the beginning of the universe. It was a cosmic crime scene, and all the evidence showed that the physics we know was insufficient. But the biggest shock was yet to come. Because Webb didn't just study individual objects, it also studied their relationships, and it found the black hole galaxy mass ratio anomaly. In the modern universe, there is a fairly constant ratio between the mass of the supermassive black holes at the centers of galaxies and the total stellar mass of the galaxy. This ratio is usually around 0.1%. That is, the black hole is 1,000th of the galaxy's mass. This ratio was thought to emerge from the co-evolution of the galaxy and the black hole over billions of years, regulating each other. But when Webb looked at the early universe, it saw that this ratio was completely overturned. In the first galaxies, black holes were reaching 1%, 10%, and in some cases, even 50% of their galaxy's mass. The black holes were disproportionately, monstrously large compared to their galaxies. It was as if the black holes formed first, not the galaxies, and the galaxies grew around them. This reverses the entire bottom-up evolution model, suggesting a top-down cosmology. It was like discovering that the chicken came from the egg, not the egg from the chicken. This discovery indicates that black holes are not just a part of galaxies, but perhaps the driving force, the main engine of galaxy formation. This also opens the door to the most radical theories, such as that black holes have existed as primordial black holes from the very beginning of the universe and have shaped its structure. This mass ratio anomaly is perhaps Webb's most profound, most philosophical discovery, because it has the potential to change the direction of the arrow of causality in the universe. Therefore, the picture Webb presents to us is no longer just a theory full of cracks, but a completely shattered model. The most distant galaxy we've seen, JADES-GS-Z-13-0, questions time itself. The impossible-to-exist Schrödinger's galaxies question matter itself. The record-breaking oldest black hole, Sears 1019, questions growth itself. And the overturned mass ratio questions causality itself. These are successive cosmic earthquakes, each one more shattering than the last. And we are right at the center of these earthquakes. Science has not been this exciting, this uncertain, and this open to new possibilities for decades. Because these discoveries are forcing us not just to find new answers, but to ask our most fundamental questions again. So, is there an order in all this chaos? A logic among these impossibilities? A single unifying theory that could bring all these shocking discoveries together? Of cosmology. For years, we were told that the early universe was a dense, lumpy place, rapidly coming together under the gravity of dark matter. This cold, dark matter model was very successful in explaining how the tiny fluctuations in the CMB turned into today's giant galaxy clusters. The model predicted that small-scale fluctuations should be much more numerous than large ones, which meant that the early universe should have been extremely noisy and lumpy. But Webb's observations seem to tell a different story. The distribution and structure of early galaxies are much less lumpy, much more orderly than expected. This has revived alternative theories like hot or warm dark matter. In these theories, dark matter particles move faster and suppress the formation of small-scale structures, creating a smoother early universe. If this is true, it would not be just a minor adjustment. It could change our most fundamental understanding of the nature of the mysterious matter that makes up 85% of the universe. If dark matter is not cold and lazy as we thought, this could explain why galaxies formed so quickly and orderly. This could be the missing piece of the puzzle. But what if the problem is not just matter? What if the problem is the rules governing the universe itself? Webb's findings are so extreme that some physicists are raising an even more radical possibility: the laws of gravity. Einstein's general theory of relativity has passed every test for over a century. It has never been tested on large scales in the earliest ages of the universe. What if gravity behaved differently when the universe was very young and dense? This idea is being explored in theories like modified Newtonian dynamics, MOND. These theories suggest that gravity acts stronger than Einstein predicted at very low accelerations, that is, on the outer edges of galaxies or in giant cosmic voids. If this is true, we might not need dark matter to explain the rotation of galaxies. And more importantly, if gravity was stronger in the early universe, this could explain why matter came together so quickly to form those massive structures. This is a highly speculative area. But Webb's data is forcing us to question even the theories we hold most sacred. The telescope might be telling us not only what the universe looks like, but also what rules it plays by. and maybe those rules are much more flexible than we thought. This is the most exciting moment in science, the moment when all the old maps have become useless and we are standing on the shores of an unknown continent. And on this unknown continent, perhaps the most surprising landscape is the tendency of the universe itself to develop a consciousness. This is not a teleological argument, it is an observation. Webb has shown how early heavy elements necessary for life like carbon, oxygen, and iron, appeared. Theories said that these elements should have been slowly accumulated by generations of stars over billions of years. But Webb detected the presence of these elements even when the universe was just a baby. This shows that the universe is in an incredible hurry to achieve chemical complexity. It's as if the fundamental laws of the universe are promoting a progression from simple hydrogen and helium to complex, life-enabling molecules. This cosmic evolution process may not be just biological, but also chemical and physical. This brings us to a deep question. Is life a rare accident or an inevitable consequence encoded in the fundamental structure of the universe? Webb's findings seem to give a slight hint towards the latter. If the building blocks of life have been so abundant and widespread from the very beginning of the universe, then it is likely that life is much more common in the universe than we thought. We may not be a lonely island in this cosmic sea. Maybe we are just one of countless islands, and Webb is the binoculars showing us the coastlines of the other islands for the first time. This thought requires us to be both excited and humble. We are not special, but we are part of a larger, richer cosmic story. All these revolutionary ideas bring us to one final, perhaps the most shocking possibility. What if the Big Bang wasn't a beginning? What if it was just a transition? The standard model says that the universe started from a single point, a singularity. But this singularity is a point where physics breaks down. Maybe this is a limit of our theory, not reality itself. Models like cyclic cosmology or bouncing universe suggest that our universe is a bounce born from the collapse of a previous universe. According to this idea, the universe goes through an endless cycle of expansion and contraction. Each Big Bang is the end of the previous one and the beginning of the next. This could explain the extreme early maturity that Webb found. Maybe those impossible galaxies didn't start from scratch with our universe. Maybe they were built on the remnants, structures, and information of a previous universe. This means that the universe has a memory. This is a speculation close to philosophy, almost impossible to test right now. But Webb has brought us so close to that beginning moment that we are now forced to ask what might be behind the curtain. Every early galaxy, every early black hole that Webb finds adds a small piece of evidence to this radical idea. They may be the whispers of a story written before our story began. This overturns our most fundamental understanding of the nature of time. We may be a single wave in an infinite ocean. This is the picture Webb presents to us. Cracking old theories, bold new ideas, and at the center of it all, the fact that the universe is much stranger, much more complex, and much more interesting than we thought. But now, after this dizzying pace, it's time to pause and take a breath. What do all these discoveries, all these numbers, all these theories mean for us, for humanity, when they come together? And because this story is not just about galaxies and black holes, this story is about our place, our meaning, and our destiny. And what Webb has to say to us about this could perhaps change everything. But now it's time to stop and think. Let's slow down for a moment after this dizzying pace, these shocking discoveries. Because when all these discoveries, all these numbers and theories come together, they take us beyond cosmology, to the deepest questions of our existence. This is not just a story about galaxies and black holes. This is a story about our place, our meaning, and our destiny. And what Webb whispers to us about this is perhaps even more profound than its most surprising discoveries. Now we face the most important question. Who are we in all of this? And where is our place? The first and most overwhelming contrast we encounter on this journey is that dizzying chasm between greatness and smallness. On one hand, there is a universe of literally unimaginable size that Webb shows us. The diameter of the observable universe is 93 billion light-years. It contains hundreds of billions, perhaps trillions of galaxies. And each galaxy, like our Milky Way, is home to hundreds of billions of stars. Webb shows us not only the most distant shores of this infinite ocean, but also the deepest depths of time, 13.4 billion years ago. It's impossible to even visualize these numbers in our minds. On the other hand, there's us, standing on a tiny piece of rock orbiting a star we don't even know the name of, in a galaxy we don't even know the name of, with our average height of 1.7 meters. We are one of the smallest measurable parts of this universe. This is the tragic truth. The truth of how physically insignificant we are in the face of this infinity. We will never be able to go to those galaxies we see. We will never be able to touch those stars. Their light took billions of years to reach us, and it will take an eternity for us to reach them. This holds a deep melancholy, like a child seeing a grain of sand on the other side of the ocean, but knowing they can never reach it. But, right here, there is a beautiful truth shining within that tragedy. Yes, we are physically small. Yes, we will never be able to go to those galaxies. But our minds can. We can understand them. We can understand how they formed, why they shine, why they look the way they do. Inside our 1.7 meter bodies, we carry a consciousness that can comprehend a universe 93 billion light-years wide. This is not proof of our smallness, but of our greatness. We may be the smallest part of the universe, but we are also the part where it understands itself, thinks about itself. You are living this paradox within yourself. You are less than even a tiny dot in this massive universe. But you are also a being who can think about that universe, who can imagine it, who can ask questions about it. Your mind can travel faster than the light of those most distant galaxies. That's why the infinity that Webb shows us is not there to crush us, but perhaps to remind us of our potential. And this journey confronts us with a second, more personal contrast: permanence and transience. On one hand, there is a universe that has a history of 13.8 billion years and will continue to exist for trillions more. Those first galaxies we saw may have long since died by the time their light reached us, but new ones have taken their place. Stars are born and die, galaxies merge and change, but the universe itself is permanent. It is time itself. On the other hand, there is our short life, an average life of 80 years. On the cosmic timeline, this is less than a blink of an eye. If the 13.8 billion year history of the universe were compressed into a calendar year, all of recorded human history would correspond to the last few seconds of the last minute. Your life and mine would be nothing more than a momentary flash within that last second. This is the second tragic truth: how transient we are in this infinite ocean of time. We are just momentary spectators of this grand cosmic play. We enter the stage, we stay for a very short time, and then we disappear. This creates that deep sadness at the core of our existence, knowing how precious but also how fleeting every moment is. But, again, there is a beautiful truth hidden in this tragedy. Yes, we are transient, but it is this very transience that gives meaning to the moment we live in. If we had an infinite life, no moment would be special. No decision would matter. But, because our time is limited, every moment, every choice, every experience becomes priceless. The 13.8 billion year history that Webb shows us makes our short moment even more meaningful. Because we are the result of those billions of years of evolution, those star explosions, those galaxy mergers. We are that short but intense moment when the universe experiences itself. Our existence gives meaning to that long and silent history. You too live this paradox every day. Your time is also limited, but this limitation makes your story an epic, not a tragedy. Every day, you have the opportunity to write a new page of that epic. And Webb shows us what a huge book that epic is a part of. We may be just a momentary flash, but that flash has the potential to illuminate even the darkest corners of the universe. This brings us to a third and perhaps most comforting contrast: loneliness and connection. Webb's images can at first create an overwhelming sense of loneliness. There are millions of light-years of empty space between galaxies. Each star, trillions of kilometers away from its nearest neighbor, spins in its own silence. The universe seems to be a vast emptiness, with lonely islands scattered within it. This is the tragic truth of cosmic loneliness. Our little blue planet is like a single point of light in this vast darkness. We do not know if there is another conscious life form. Perhaps we are completely alone in this galaxy, even in this universe. This thought can create a deep sense of isolation and fragility. The feeling that the universe is indifferent to us, that our existence means nothing to it. But, when we look more closely, Webb tells us a completely different story. It is the story of connection. Yes, there are vast voids between galaxies, but they are parts of a giant cosmic web, connected to each other by invisible threads of dark matter. Everything interacts gravitationally with everything else, and more importantly, we are chemically connected. The carbon atoms that make up your body were forged in the core of a star that died billions of years ago. The oxygen you breathe came from another supernova. The iron flowing in your veins is the legacy of yet another star. We are literally stardust. We are the gathering of pieces from different corners of the universe on this small planet. This is the deepest proof that we are not alone. We are not separate from the universe. We are the universe itself. This is the beautiful truth, the truth of connection. You too can feel this connection every moment. You are connected not only to your family and friends, but also to those stars that died billions of years ago. Your existence is the result of a continuous story that has been going on since the very beginning of the universe. Those distant galaxies that Webb shows are your distant relatives. They are your origin, your past. That's why when we look at those images, we are not looking at a stranger, but at our own family album. And this is perhaps the greatest consolation. In this vast and sometimes frightening universe, we are never truly alone. But there is a deeper layer to this connection. Knowledge itself, and therefore this journey brings us to one of the most fundamental contrasts, the tension between the whole and the part. On one hand, there is the idea of the whole, the ultimate explanation for everything, a complete picture that tells how the universe began, what laws it follows, and where it is ultimately going. That ultimate theory that science and philosophy have been chasing for thousands of years. On the other hand, there are the things we have, parts. Every image Webb sends us, every spectrum, every data point, is just a tiny piece of that great puzzle. This is the tragic limit of knowledge. The fact that the parts can never fully represent the whole. No matter how much we learn, there will always be things we don't know, things we can't see. Like the horizon, it will recede as we approach it. The slight melancholy of never being able to fully grasp the whole is part of the human condition. It's like reading a book with missing pages. We will never fully know the end of the story. But perhaps meaning lies not in possessing the whole, but in making connections between the parts. Perhaps wisdom is not knowing everything, but being able to sense a larger pattern from the small pieces we know. Every new piece Webb gives us combines with the old pieces to reveal a new pattern, a new relationship we couldn't see before. The spectrum of the first galaxies combines with the growth rate of black holes. The distribution of dark matter combines with the expansion rate of the universe. And these connections tell us much more about the whole than a single piece ever could. We may never see the whole, but we can see its echoes, its shadows, its patterns. You live your life this way too. Every moment of your life is a part. But when you bring these moments together, when you give them meaning, when you create a story, that whole you call you emerges. You are more than the sum of your parts, so is the universe, and Webb gives us the opportunity to put those pieces together and read that great story of the universe in a richer way than ever before. And this brings us to what is perhaps the most comforting yet most daunting contrast of this philosophical journey, chance and inevitability. On one hand, there is that incredible chain of coincidences at the foundation of our existence. Those tiny density differences in the Big Bang that were just right to allow galaxies to form. The physical constants that have such incredibly precise values that allow complex atoms like carbon to form. The Earth being at that perfect distance from the Sun called the habitable zone. And at the end of billions of years of evolution, the emergence of a consciousness that could build this telescope. If even one link in this chain had been different, we would not be here. This shows how much our existence hangs by a thread. It's such an improbable coincidence. It's like winning a cosmic lottery. But this thought can also create a deep sense of meaninglessness. If everything is just a coincidence, then our existence has no deep meaning, no purpose. We are just the result of a lucky chemical reaction. This is the tragic void brought by chance. On the other hand, there is that strange sense of inevitability that Webb whispers to us. The fact that complexity and order emerged so quickly from the very beginning of the universe, the formation of galaxies, stars, heavy elements much earlier than theories predicted, as if they were in a hurry to appear. This evokes the feeling that the universe has had a tendency, a direction towards complexity, and the emergence of consciousness from the very beginning. This is not a teleological argument, one directed towards a purpose. It is just an observation. The universe seems to be a system set up to progress from disorder to order, from simplicity to complexity. Perhaps our existence is not a coincidence, but an inevitable result of this fundamental cosmic tendency. But these two ideas, chance and inevitability, do not have to be mutually exclusive. Perhaps the universe is rolling a die full of possibilities, but that die is loaded. The probability of certain outcomes, namely the emergence of complexity and consciousness, is higher than others. Perhaps we are both the lucky winners of a lottery ticket and the buyers of a lottery that had a tendency for us to win from the very beginning. This thought gives our existence both the miraculous uniqueness of chance and the deep-rooted meaning of inevitability. You carry both in your own life. Many events in your life seem random, but when you look back, you see that all those coincidences have put you on an almost inevitable path that made you who you are. You are both the product of a series of coincidences and a being who writes their own inevitable story within those coincidences. And Webb suggests to us that the story of the universe may be like this too, both lucky and meaningful, both random and inevitable. At the end of this long and deep journey, we find ourselves in the same place again, but with a completely different perspective. Under our blankets, in the silence of our room. But we no longer just feel small in the face of the overwhelming size of the universe. We question. We understand. We make connections. Webb didn't just show us new worlds, it taught us to look at our own world with new eyes. This journey has shown us that the universe has been faster, more complex, and more orderly than expected from the very beginning. This has shattered our old, orderly stories. But, in their place, it has put a much more exciting, much more mysterious narrative. This is not just a scientific revolution, it is a revolution of consciousness. It is a moment when humanity's understanding of its place in the universe is radically changing. We now know that we are not just temporary inhabitants of this universe, but also its memory, its consciousness, and its search for meaning. We are the beings through which the universe thinks about itself. As we approach the end of this journey, all those shocking discoveries, technical details, and philosophical depths are distilled into one simple but powerful truth. We are part of a much bigger story than we thought, and this story has only just begun to be written. The Webb telescope has only opened the first page of this story. Even that first page was enough to show that the universe is stranger, more beautiful, and more miraculous than anything we could have imagined. And now, armed with this knowledge, enlightened with this new consciousness, we are ready to take the final step of our journey, to put all these pieces together and look at the great legacy, the ultimate message that Webb has left us. Because this message is not just about the stars, this message is about us. But on this journey, Webb didn't just show us the past. Einstein's theories predict hidden doors in the fabric of space-time that could open to the past. black holes and wormholes. And now these thoughts bring us to the next, deeper question, to that delicate balance between knowing and being. Because, on one hand, there is the immense knowledge we have gained thanks to Webb. We know the 13.8 billion year history of the universe, the chemical composition of the most distant galaxies, the mass of the oldest black holes. For the first time in human history, we can answer the most fundamental questions about our origin with observational evidence. This is the triumph of the mind, the triumph of curiosity, science, and technology. On the other hand, there is the question of what we will do with this knowledge. How does this knowledge change our daily lives? When we wake up in the morning, on our way to work, while talking with our loved ones, what does knowing the redshift value of the most distant galaxy change? This is the tragic truth of knowledge. Knowing does not always mean being. Understanding the theory of something is not the same as experiencing it. Knowing a love poem by heart is not the same as being in love. Knowing how big and old the universe is does not mean feeling that size and age at every moment. The cosmic reality we grasp with our minds can often remain disconnected from the small, human reality that our hearts and souls experience. But perhaps this disconnection is not a tragedy, but an opportunity. The beautiful truth is our potential to unite these two worlds. We can bring that great cosmic knowledge into our small, personal moments. When we look at a tree, we can see not just a tree, but a collection of carbon atoms forged in the core of a star billions of years ago. When we watch a sunset, we can think not just of beautiful colours, but of the Rayleigh scattering of starlight passing through our planet's atmosphere. This is not to demystify life, but on the contrary, to add a deeper, richer magic to it. Science does not kill mystery, it feeds it. You too can unite these two worlds every day. You are both a human dealing with the small worries of daily life, and a being who knows the deepest secrets of the universe. You can see this knowledge not as a burden, but as a gift. This knowledge can give you perspective. It can remind you how transient your small problems are on that grand cosmic stage. And at the same time, it gives you a responsibility. The responsibility to live your life more meaningfully, more fully, as a being with such a rare, such a precious consciousness. And this responsibility brings us to another powerful contrast, that fine line between power and fragility. On one hand, there is our incredible technological power that allowed us to build Webb. We are a species that can design a $10 billion telescope, send it millions of kilometers away, and control it with atomic precision. We have understood the laws of physics, and we use them to uncover the greatest secrets of the universe. This is a testament to our collective intelligence and perseverance, a symbol of humanity's power. On the other hand, there is the incredible fragility on which this power rests. The Webb telescope had 344 single points of failure. If just one of them had gone wrong, the entire project would have failed. And more importantly, the planet that hosts all this technology rests on such a delicate balance. The chemistry of our atmosphere, the temperature of our oceans, the health of our ecosystems, all hang by a thread. No matter how powerful we are on a cosmic scale, we are so fragile in our own home. This is the tragic truth of our power. Even our greatest achievements show how vulnerable we are to the smallest mistakes or the slightest negligence. We can see the beginning of the universe on one hand, while being careless enough to bring about our own end on the other. But this fragility can also be the source of our greatest strength. The beautiful truth is the potential for our awareness of this fragility to make us wiser, more responsible, and more compassionate. When we understand how big the universe is and how small we are, we understand that we need to hold on to each other and to this planet more tightly. Because, in this vast darkness, all we have is each other and this little blue dot. Every image Webb sends us is not just a scientific datum, but also a warning. It is a reminder of how rare, how special, and how worthy of protection what we have is. You too carry this power and fragility within you. You have the potential to achieve incredible things, but you are also a human who can be hurt, who can make mistakes. When you accept your fragility, not as a weakness, but as a sign of humanity, you can be more understanding towards both yourself and others. Because we are all in the same boat. We are all journeying on this small, fragile planet in that vast and indifferent universe. And this common journey brings us to one final contrast, perhaps the most hopeful one, that endless dance between question and answer. On one hand, there are the huge questions that Webb has answered. When did the first galaxies of the universe form? What did the first stars look like? How fast did the first black holes grow? We now have concrete answers to these questions that have been asked for decades, even centuries. This is the progress of science. Every answer is a new stone added to the mountain of human knowledge. On the other hand, there are the new, deeper questions that each answer gives rise to. Webb closed one door, but opened thousands of new ones. Why did everything happen so fast? Why was it so orderly? Is dark matter not what we thought it was? Are the laws of gravity different? Was the Big Bang really a beginning? This is the tragic but also magnificent truth of science. The quest for knowledge never ends. Every time we reach a peak, we see that there is a higher peak ahead of us. We will never have all the answers. There will always be a mystery, always an unknown. But perhaps the meaning of the journey is not in arriving, but in being on the way. The beautiful truth is that our ability to ask questions may be more important than finding answers. Answers tell us what we know, but questions tell us what we can be. Questions are the engine of our curiosity, our imagination, and our infinite potential. Webb is not just an answer machine, it is also a question generator, and it forces us to ask questions we never even thought to ask before. This is the essence of being human, to ask questions, to wonder, to try to understand. You live your life with this dance too. You find new answers every day, but you also encounter new questions every day. Do not be afraid of your questions. They are what keep you alive, what make you grow, what make you who you are. Do not be afraid of the darkness of the unknown, because that darkness is where new discoveries, new adventures, and new meanings are born. And Webb has given us a new candle to look into that darkness. The path that candle illuminates is only the beginning. This story is not just about what Webb found, it is also about what those findings trigger within us. And this brings us to one final, most personal thought. And therefore, this journey brings us to one of the most fundamental contrasts, the tension between the whole and the part. On one hand, there is the idea of the whole, the ultimate explanation for everything, a complete picture that tells how the universe began, what laws it follows, and where it is ultimately going. That ultimate theory that science and philosophy have been chasing for thousands of years. On the other hand, there are the things we have, parts. Every image Webb sends us, every spectrum, every data point, is just a tiny piece of that great puzzle. This is the tragic limit of knowledge, the fact that the parts can never fully represent the whole. No matter how much we learn, there will always be things we don't know, things we can't see. Like the horizon, it will recede as we approach it. The slight melancholy of never being able to fully grasp the whole is part of the human condition. It's like reading a book with missing pages. We will never fully know the end of the story. But perhaps meaning lies not in possessing the whole, but in making connections between the parts. The beautiful truth is the power of knowledge to perceive a larger pattern by connecting the parts. Every new piece Webb gives us combines with the old pieces to reveal a new pattern, a new relationship we couldn't see before. The spectrum of the first galaxies combines with the growth rate of black holes. The distribution of dark matter combines with the expansion rate of the universe. And these connections tell us much more about the whole than a single piece ever could. We may never see the whole, but we can see its echoes, its shadows, its patterns. You live your life this way too. Every moment of your life is a part. But when you bring these moments together, when you give them meaning, when you create a story, that whole you call you emerges. You are more than the sum of your parts. So is the universe. And Webb gives us the opportunity to put those pieces together and read that great story of the universe in a richer way than ever before. And this brings us to what is perhaps the most comforting, yet most daunting contrast of this philosophical journey: chance and inevitability. On one hand, there is that incredible chain of coincidences at the foundation of our existence. Those tiny density differences in the Big Bang that were just right to allow galaxies to form. The physical constants that have such incredibly precise values that allow complex atoms like carbon to form. The Earth being at that perfect distance from the Sun called the habitable zone. And at the end of billions of years of evolution, the emergence of a consciousness that could build this telescope. If even one link in this chain had been different, we would not be here. This shows how much our existence hangs by a thread. It's such an improbable coincidence. It's like winning a cosmic lottery. But this thought can also create a deep sense of meaninglessness. If everything is just a coincidence, then our existence has no deep meaning, no purpose. We are just the result of a lucky chemical reaction. This is the tragic void brought by chance. On the other hand, there is that strange sense of inevitability that Webb whispers to us. The beautiful truth is the universe's tendency towards complexity and the rapid emergence of order from the very beginning. The formation of galaxies, stars, heavy elements much earlier than theories predicted, as if they were in a hurry to appear. This evokes the feeling that the universe has had a tendency, a direction towards complexity and the emergence of consciousness from the very beginning. This is not a teleological argument, one directed towards a purpose. It is just an observation. The universe seems to be a system set up to progress from disorder to order, from simplicity to complexity. Perhaps our existence is not a coincidence, but an inevitable result of this fundamental cosmic tendency. But these two ideas, chance and inevitability, do not have to be mutually exclusive. Perhaps the universe is rolling a die full of possibilities, but that die is loaded. The probability of certain outcomes, namely the emergence of complexity and consciousness, is higher than others. Perhaps we are both the lucky winners of a lottery ticket and the buyers of a lottery that had a tendency for us to win from the very beginning. This thought gives our existence both the miraculous uniqueness of chance and the deep-rooted meaning of inevitability. You carry both in your own life. Many events in your life seem random, but when you look back, you see that all those coincidences have put you on an almost inevitable path that made you who you are. You are both the product of a series of coincidences and a being who writes their own inevitable story within those coincidences. And Webb suggests to us that the story of the universe may be like this too, both lucky and meaningful, both random and inevitable. At the end of this long and deep journey, we find ourselves in the same place again, but with a completely different perspective. Under our blankets, in the silence of our room. And we no longer just feel small in the face of the overwhelming size of the universe. We question, we understand, we make connections. Webb didn't just show us new worlds, it taught us to look at our own world with new eyes. This journey has shown us that the universe has been faster, more complex, and more orderly than expected from the very beginning. This has shattered our old, orderly stories, but in their place, it has put a much more exciting, much more mysterious narrative. This is not just a scientific revolution, it is a revolution of consciousness. It is a moment when humanity's understanding of its place in the universe is radically changing. We now know that we are not just temporary inhabitants of this universe, but also its memory, its consciousness, and its search for meaning. We are the beings through which the universe thinks about itself. As we approach the end of this journey, all those shocking discoveries, technical details, and philosophical depths are distilled into one simple but powerful truth. We are part of a much bigger story than we thought, and this story has only just begun to be written. The Webb telescope has only opened the first page of this story. Even that first page was enough to show that the universe is stranger, more beautiful, and more miraculous than anything we could have imagined. And now, armed with this knowledge, enlightened with this new consciousness, we are ready to take the final step of our journey, to put all these pieces together and look at the great legacy, the ultimate message that Webb has left us. Because this message is not just about the stars. This message is about us. On this journey with Webb, we have looked into the most ancient past of the universe. I didn't tell you a secret. We don't have to look only at the past. Einstein's theories predict hidden doors in the fabric of space-time that could open to the past, black holes and wormholes. On our next journey, we will dive into the real physics of time travel. Is it possible to change the past? Are you ready?